And welcome to our discussion of how Fourier coefficients and ordinary differential equations interact. We will begin with a hugely useful property of Fourier coefficients. I cannot overstate how powerful this next result is. If I have a function f from the interval minus pi to pi into the complex plane that is 2 pi periodic and C1, so f of minus pi equals f of pi, f is continuous, f is differentiable, and f's derivative is continuous, then the kth Fourier coefficient of f prime, in other words, f prime hat at k, is equal to ik times f hat of k. In other words, we have a fairly simple relation between the kth Fourier coefficient of f prime and the kth Fourier coefficient of our original function f. Let's prove this. We start by looking at what f prime hat of k is. In the case of this 2 pi periodic function f, it is 1 over 2 pi times the integral from minus pi to pi of f prime of x times e to the minus ikx dx. We want to turn this integral into something involving f because we want to get the f hat on the right side of the equal sign. So let's integrate by parts. We'll put u equal to e to the minus ikx. So du is minus ik, e to the minus ikx dx. Put dv equals f prime of x, and v equals f of x. That's really the only natural thing to do in this integral. It's a product of two things, so we often think of integration by parts. And we don't know that we have more derivatives on f. F is only 1 times differentiable, so it makes sense to put the dv factor to be f prime of x. And so this integral from minus pi to pi, f prime of x e to the minus ikx dx, turns into the expression f of x times e to the minus ikx evaluated at x equals pi, minus that evaluated at x equals minus pi. And then we'll subtract off the integral from minus pi to pi, f of x times minus ik times e to the minus ikx dx. And so this turns into f of pi times e to the minus ik pi minus f of minus pi times e to the ik pi plus ik times the integral from minus pi to pi, f of x e to the minus ikx dx. And so we're just careful about all our plus and minus signs going from one line to the next. And we should like this because we're now seeing an integral of f of x against e to the minus ikx. So we assumed that f was 2 pi periodic, f of pi equals f of minus pi. This tells us that our first two terms in the integration by parts expression, f of pi times e to the minus ik pi minus f of minus pi times e to the ik pi, this is equal to, let's pull out that f of pi. So f of pi and f of minus pi are the same. I've pulled out f of pi. It's equal to f of pi times e to the minus ik pi minus e to the ik pi. Now that may or may not look better, but in fact it is. If we think about some of our complex trig functions, when do we have e to a minus power minus e to the power? If we multiply and divide by minus 2i, this turns into minus 2i f of pi times e to the ik pi minus e to the minus ik pi over 2i. And that, of course, is our complex sign at k pi. So this is minus 2i f of pi times sine of k pi, and that is equal to 0 regardless of what f of pi is. And so the kth Fourier coefficient of f prime, f prime hat of k, is equal to, going back to my integration by parts, 1 over 2 pi times the integral from minus pi to pi of f prime of x e to the minus ikx. That's the definition. And integration by parts tells us this is 1 over 2 pi times ik, integral minus pi to pi, f of x e to the minus ikx. And if I just flip around the ik and the 1 over 2 pi, this is ik times f hat of k. And so my identity has been proved. So what really mattered in this proof in this calculation. First, I needed to be able to integrate by parts, so I needed to assume that f was differentiable, and for the integral to exist, I assumed that f prime was continuous. And just above on this slide, I really did need that 2 pi periodicity for f to be able to get those boundary terms from integration by parts to be 0. Now, why are we doing this for 2 pi? We've always done our Fourier series as much as possible for generally 2p periodic functions. So why not a 2p periodic function here? The answer is simple. It is too complicated. If you were to repeat this calculation for a 2p periodic function, you would get a factor of p somewhere in the expression, and that is just confusing and too hard to keep track of. Well, maybe it's not too hard to keep track of, but I don't feel like doing it. Perhaps more importantly, as you'll see in this week's exercises, if you're trying to do a problem, a differential equations problem, with a 2p periodic function, very often you can rescale the problem so that you're working with a 2 pi periodic function. And you change your differential equation a little bit, but you're able to work with just 2 pi periodicity and this nice simple relation f prime hat of k equals ik f hat of k. So you'll see that in the exercises. And a way to remember this in words is that differentiation is multiplication on the Fourier side. We go from f prime hat of k, and that becomes ik f hat of k. So the derivative f prime turns into multiplication by ik. And this turns out to make a lot of problems, as we'll see in this video, in ordinary differential equations, and then subsequently in partial differential equations, a lot easier or more transparent on the Fourier coefficient side. We'll need some new function spaces and some new notation. So I'll put Cn periodic of the interval minus pi to pi to be all functions f in Cn of minus pi to pi, such that f of minus pi equals f of pi. So remember, Cn, these are the n times continuously differentiable functions on the interval minus pi to pi. So derivatives 1 through n of f exist, and the nth derivative is continuous. And I'll also put C periodic of minus pi to pi is C periodic 0 of minus pi to pi. So C periodic of minus pi to pi, these are the continuous functions on minus pi to pi that are 2 pi periodic. So I'm always assuming that f of minus pi equals f of pi in these function spaces, so I can always invoke the previous result relating the derivative coefficients to the original function's coefficients. Now let's do an example. Let's use Fourier series to solve a very simple, very familiar differential equation, f double prime plus f equals g of x, and we'll do this looking for a function f in C2 periodic, where we're given a forcing function g in C periodic. And we'll work backwards, and we'll suppose we'll have a solution f and see what we could do. Now this differential equation shouldn't give us too much pause, right? Because f double prime plus f equals g, it's constant coefficient linear second order. We could solve this with variation of parameters. Except for the interesting little fact that we're working now with 2 pi periodic functions, which will add a bit of a wrinkle to our solution. So suppose I have a solution f. What can I figure out about f? Can I try to get some sort of formula for f, and then maybe prove that that formula is actually a solution? Well, what do I know about f? The only thing I know about it is that it solves this differential equation. So say I put h of x equal to the left side of this equation. H of x is f double prime of x plus f of x. What does that tell me? Then h of x has to be equal to g of x. So if two functions are equal, then their Fourier coefficients have to be equal for all k. We know sadly from last week that the reverse is not true. Maybe h hat of k equals g hat of k for all k, but maybe h and g are different functions. But here I'm assuming h equals g, so then h hat equals g hat. So what does this mean? Well, f double prime hat of k plus f hat of k equals g hat of k. Fourier coefficients are linear just because the integral is linear. So f hat of k, there's nothing really to do there. What is f double prime hat of k? Well, I'll use my previous result on interchanging derivatives and multiplication by ik. F double prime hat of k is ik f prime hat of k. So I killed off one prime there and turned that into multiplication by ik. I'm left with a prime, so this becomes ik squared f hat of k, or minus k squared f hat of k. And so, if I have f double prime plus f equals g of x, that means that minus k squared f hat of k plus f hat of k equals g hat of k. Or if I just factor the left side a little, 1 minus k squared times f hat of k equals g hat of k. So now I have a relation between f hat and g hat. And my goal, remember, is to figure out some sort of formula for f, maybe equivalently some sort of formula for f hat of k. And this seems to get me pretty close to that. But first, let's think about what this relation is telling us. If I'm able to solve our problem, f double prime plus f equals g, with f in C2 periodic and g in C periodic, if I'm able to do that, what does that tell me? I need to have 1 minus k squared f hat of k equals g hat of k. Now it almost looks like I could solve for f hat, and I will in a moment, but what does this tell us about g hat? Say I take k equal to plus or minus 1. This forces g hat at plus or minus 1 to be equal to 0, because the left side of this equality, 1 minus k squared f hat equals g hat, no matter what f is, if I plug in k equals plus or minus 1, that left side is 0. So if I'm able to solve the problem f double prime plus f equals g, I must have g hat of plus or minus 1 equals 0. So I cannot solve this ODE for all possible functions g. Only those at minimum with g hat of plus or minus 1 equals 0. This is not what variation of parameters tells us, right? G is a continuous function. It's continuous and 2 pi periodic. So as long as my right-hand side is continuous, variation of parameters says I should be able to solve f double prime plus f equals g. But look a little deeper at what I'm trying to do. I don't just want a C2 function f to solve this problem. I want a C2 periodic function f to solve this problem. So this 2 pi periodicity of f constrains us a little more to what non-homogeneities g we can allow. Really, we're solving a boundary value problem here. We want f double prime plus f equals g of x, and f of minus pi equals f of pi. And as we've seen several times throughout the course, and as we will see in more detail in the coming weeks, boundary value problems can have much trickier behavior than initial value problems. So, suppose we do have our forcing function g in C periodic with g hat of plus or minus 1 equals 0. Then can I solve the equation already? Yes. So what does f have to do? We need 1 minus k squared f hat of k to be equal to g hat of k. This tells us that f hat of k equals g hat of k over 1 minus k squared for obviously k not equal to plus or minus 1. So this gives us a formula for f hat of k. In the problem, you start out trying to solve f double prime plus f equals g. I tell you what g is, you have to tell me what f is. Well, I've told you f hat of k equals g hat of k over 1 minus k squared. So I should expect that f of x can be written as its Fourier series. After all, I'm looking for a C1 solution to the problem, so I'd want to be able to write f of x equals the sum from k equals minus infinity to infinity of f hat of k times e to the ikx by our convergence theory from last week. And this says the sum should be the sum from k equals minus infinity to infinity, excluding k equals plus or minus 1, of g hat of k over 1 minus k squared times e to the ikx. So after that second equality, you tell me what g is, I know what everything in this sum is. So in principle, I've been able to define f as its Fourier series. I worked backwards and assumed that I had a solution, and I figured out what the Fourier series has to be. Now, what happens at k equals plus or minus 1? I've excluded them from the sum for good reason, to avoid dividing by 0. Well, they're free coefficients. We can't determine what happens at k equals plus or minus 1 without more information in the problem, maybe some initial conditions. So a more general solution to our problem would be the sum from k equals minus infinity to infinity, excluding k equals plus or minus 1, of g hat of k over 1 minus k squared times e to the ikx, plus an arbitrary constant c1 times e to the ix, plus an arbitrary constant c2 times e to the minus ix. And this is exactly what we expect for the ODE f double prime plus f equals g, since e to the ix and e to the minus ix are a fundamental solution set for this ODE. We should be able to add in an arbitrary linear combination of these two functions. So this is my general solution represented in terms of Fourier series. And other than my restriction on what g has to be, this looks a lot like what I would get in the past. A particular solution, this big series monster, plus a linear combination of the fundamental solution set. Nonetheless, this is a formal solution. Let's say that f of x is the series part. I'm going to call that f0 of x, plus c1 e to the ix, plus c2 e to the minus ix. When people say formal in math, I've used this term already throughout the course, and I'll use it again a lot, they just mean an expression, a symbolic thing. We're not talking about whether or not it converges for a given x. But of course, if f is to be well defined as a function, if it is to converge, if it is to be continuous and differentiable, well, we better move beyond formalities. So does this series f0 of x converge for a given x? Well, it's not really a Fourier series of g anymore, even though there are g hats in there. I've got this 1 minus k squared. How could I guarantee the convergence of f0 of x as a series in the complex numbers for a given x? Well, remember, we have a Sobolev inequality. So if g is continuous and 2 pi periodic, then we know that g hat of k, its Fourier coefficient at k, is less than or equal to 1 over 2 pi times this integral minus pi to pi modulus g of x. And that, because g is continuous, is less than or equal to the maximum of g on the interval minus pi to pi, which I'll call c. So g is continuous, g has to have a max on this closed bounded interval. So then if I look at the terms of my sum f0 of x, and I take their modulus, well, modulus of e to the ikx is 1, so I just get modulus of g hat of k over 1 minus k squared, and that's bounded by this uniform constant c, independent of k, over the denominator 1 minus k squared. And I like this denominator. The comparison test will tell me that f0 of x converges for all x, and so I have no worries about f being well defined pointwise in x by this series f0 of x. Now, is f0 continuous and differentiable? So the series converges, so it makes sense to talk about the expression f of x. Can I differentiate that? Is it continuous? Yes, but you do need quite a bit more theory of uniform convergence of series and sequences of functions, which is beautiful and rich and just a little beyond our scope of the course due to time constraints. So yes, take my word for it that f0 is continuous and differentiable, and we get back a good solution to our familiar ODE using Fourier series methods.